He's not here today. Victor will tell us about online discrepancy minimization.
Thanks, Serge. So first I'll give an introduction about discrepancy and then some motivation. So by the way, this is my first Blackboard talk ever. So you're my guinea pigs. So here the standard setting is the following. So given a set system, I'll denote by S. So it has some sets S1 through Sn. Here we're going to define the discrepancy of S. So let's say these sets are all in the integers from 1 through t. The discrepancy of S will be defined as the minimum. So it's the minimum over all colorings. So colorings defined as a function from the universe t to plus minus 1. And then you look at what is the most imbalanced set in this respect to this coloring. So I need to take the maximum over all sets. Of this coloring, and then I sum over all the elements in the set. So here's my favorite example. Consider the funnel plane. So it's this picture where you have this triangle, and there's 7 lines and 7 points. So I've drawn 6 lines, and the 7th line actually looks like this. So I have 7 points. So these sets are corresponding to the lines in this picture. So there are 7 sets and 7 elements. And you can verify that no matter how I color these points of plus minus 1, say I can call this the plus 1s, maybe I color these red. And then you can say, like, no matter what I do, there's always a set that is monochromatic. So, for example, the discrepancy of the funnel plane is 3. I don't know like a direct proof. I just try all the coloring. So like you can think about, okay, what is a general bound I can get for an arbitrary set system? The standard thing people do in combinatorics, they just take random colorings. So I just color all the points uniformly at random plus minus 1. And it's not hard to check that I can get a bound using union bound and Chernoff bound to get this is at most T log n. For example, we can imagine if you had a single set, then it's kind of like square root t because it's equivalent, you have some random walk and you run it for t steps. So it takes about square root t. The extra log factor comes from Chernoff in union bound. What's interesting about this is that this is not tight. So there's a theorem of Spencer that kind of started off this field. Maybe started off is not accurate, but it's a cornerstone of this field that if the set system has as many elements as sets, then actually the discrepancy can be bounded by 6 times square root n. So it improves upon the trivial random coloring by a factor of square root log n. So here we're assuming that we have all the information ahead of time. And so in this talk, I'm going to be considering cases where I'm given the elements one by one and I need to color them as they arrive. So in order to phrase things more in the language I want, so I'll rephrase this slightly more general way, this theorem. So equivalently, so here I have set systems. I'll actually want to consider vectors corresponding to the adjacency matrix of the set system. So I'll just rewrite this in a slightly more general way. So, I mean, Spencer also proved this more general result. So here I have vectors in the unit cube. So in this previous setting, these vectors are actually just 0, 1, corresponding to whether an element belongs to a set. But here I'll consider it a more general setting. And the claim is that there exist signs so that the largest coordinate of the sign sum is bounded by the same. So just a slight restatement. So this notation here denotes the largest coordinate in absolute value, which is corresponding to this maximum here. Let's see if I can operate things. Okay, cool. So there are a number of generalizations of Spencer's theorem that remain open. And in order to motivate perhaps the rest of the talk, I'll give you one of them, which is my favorite open problem, which is also stated in Spencer's original paper called the Cumulus conjecture. It's to cumulus, but it was communicated by Spencer. So here, instead of having vectors in the unit cube, you can imagine you just have a bound on their L2 norm. So this is, I'm going to denote this as the unit ball. So this is the set of vectors for which the L2 norm is bounded by 1. And the question is, do there exist signs so that this is actually a constant? So you can think about this as a generalization of this theorem, because if vectors are in the unit cube, they have norm at most square root n. So if this is true, this it implies this. This is still open, and so the best known bound so far, well, there's this lower bound of Minsky a couple of years ago that you know, whatever the constant is has to be at least 1 plus square root u. So we don't know like good constructions. And in the upper bound sense, the best known is the Fibonacci. He showed it at most log n, square root log n. And you know, many people have tried it, and it's a very frustrating open problem. So today we're going to try to you know, tie our hands and see what can we do if if the vectors are not given to us ahead of time, but actually they're given to us one by one, what can we do in that setting? Perhaps as a way to try to understand this problem better. So this is the online discrepancy problem. So here the vectors are given to us one by one.
Can you just explain, I guess, the connection between these two? Is it just the 6 versus 1?
So this is a stronger statement. The 1 is actually up to a constant, so this squiggly means it's a, at most C. And the C, it's shown to be at least this. It's not just a constant, it's more importantly that the L2 norm is bounded here, whereas here it's the unit cube.
So you can have some large entries in this conjecture.
Yes.
That's what makes it hard.
Yes. So here we're going to be looking at the case where the vectors are given one by one. So we're going to think of it as a game with player versus adversary. And as soon as the player receives a vector, they need to pick a sign immediately. So they can't wait until the remaining vectors arrive. So let me give you the basic example here. So imagine these vectors are in the unit ball, and say I want to minimize the length as well. So so this game is actually easy to analyze. So you can imagine the game starts like this. So there's a start at 0. The adversary give me some vector, say this one, and then I need to pick either plus or minus. So I could have picked this one, but I'll just pick the plus. And then there's a choice of maybe either this vector or this vector. So maybe I pick this one. So I go here, and then the adversary can essentially keep giving me things that are orthogonal to where I am. And I basically don't have much control over what's happening to the L2 norm. So if the adversary picks the next vector perpendicular to the current position, then the L2 norm is actually always square root T. And it's easy to see that the player can also guarantee this no matter what the adversary does. Essentially, for any strategy of the adversary, maybe I'm here and the adversary gives me this option, I can always pick whatever makes an acute angle. And so the player can always guarantee that this is at most square root T. So T is the number of vectors. So even in dimension 2, this is typed by this example here. Okay, so I want to give a slightly more interesting example. So this is so here, let's consider back to the case where the vectors are in the unit cube. And let's see if we can get the same bound of square root n. So so this is due to Spencer also from 77, so it's much earlier than his theorem. So here, so I'm considering the vectors are in the unit cube. And again, I need to pick the signs as they arrive. So Spencer's idea was the following. He considered a smooth version of the maximum. So here I want to bound again the infinity norm. So he considered this function g of x, which is the hyperbolic cosine. Well, there's some parameter alpha that it's picked later. And then here the idea is that let's also define for a vector the sum of all the coordinates. So this is a vector in Rn. And so here the point is that he can control this potential function. So imagine, so take an A between 1 and -1. And then the point here is that I can bound the average value of my options. So for any x, a real number, I can write that this is, if you don't know what cosine hyperbolic means, it's, we just write here. It's like it behaves like this. And if you expand this, you get that this is equal to g of x times g of a. And for a between 1 and -1, it's always upper bounded by the value at 1. So this is at most g of x times cosine hyperbolic of alpha. And you can bound the cosine hyperbolic by some exponential function. It's not too hard to show that this is at most this. And so the point of this is that, so imagine I have some vector that denotes my current position. So maybe I'm at WT, which is the current position so far. So it's the sum, the sign sum up to this moment. And then I receive a vector V and I have two choices. So I will consider the average value of doing this or subtracting. Where here this G is denoting the sum of the coordinates. And by this inequality, I can bound this by the original value times some exponential function. So here's the algorithm. Whenever you receive a vector Vt, you just pick either plus or minus depending on which of these two quantities is smaller. And the point here is that since the average is at most this, the smallest of the two is also at most this. So you have some control over how this potential function is growing. And in the end of the day, you get something like at time step t, this is at most the original potential times what you've accumulated over the t iterations of this vector. This is g of 0, which is n. And if you look at this, well, this is at least the largest coordinate. So you can lower bound this by the exponential half of the exponential function of the largest coordinate. So if you pick alpha carefully, here turns out that the right choice of alpha is something like then this inequality will give you that the largest coordinate in the end is bounded by square root t log n. Which, is actually the same thing as if you just pick things at random. At least this is deterministic. And so the point here is that, you can do this deterministically, and also this turns out to be tight. So Spencer showed that there's actually a strategy for the adversary that also gets the same bound up to a constant factor. So actually, unlike the offline setting, you cannot remove the square root log in this case. Let's see. So this is to say that this problem is fairly well understood in this case where the adversary has the power to look at what we're doing and pick things in response. So in these two settings, we're considering the case where the adversary could have reacted to us. And the more interesting setting that we're going to look at for the rest of the talk is this so-called oblivious setting. Yeah, I'll do this first. So here, the adversary is a little restricted. So here, the adversary picks all vectors ahead of time. And we still receive the vectors one by one, and we need to pick the sign as soon as we receive them. So if the player is deterministic, for example, like this player is deterministic, an oblivious adversary could have just simulated whatever the player would have done ahead of time. So we're going to consider, randomized players. The player can toss coins.
I have a question.
Yeah.
So in this previous setup, so the adversary actually saw what I do, but I have chosen the previous.
Yes.
Does the random argument still work? You are claiming actually that's not obvious because now it's dependent on the previous bits, so it actually still works. Is that a claim?
You're saying that this random coloring would still give the same bound?
Yeah. Well, that's what you wrote over there. Then with WT.
Yeah. So this is for this approach here.
And you're saying the randomized would also work actually, or not?
I think the randomized will still work. Yes. And so for the rest of the talk, I'll consider this setting where the vectors are unit vectors. So an interesting open problem is to do this to get this bound of square root n in the oblivious setting. We don't know how to do this yet. So if the vectors are in the unit cube, we don't know how to get constant times square root n in this oblivious setting. So that's why I'm going to instead focus on something we know a little more about. So it's the case where the vectors are in the unit ball. So I want to give some background. I'll review a few works. It's a couple works actually due to Young and others. So the first algorithm that works for this oblivious setting, well, before this, there have been other papers that dealt with the case where the vectors are coming from some distribution that is known. But here we're going to look at this case where the oblivious adversary is not restricted to just sampling the vectors from a single distribution. They can do whatever they want ahead of time and give to us. So this is the first paper that got a non-trivial bound for this setting was the self-balancing random walk. So this is due to always Lusani. And so here's the idea. So we're gonna still keep track of the position. So let's still keep the same notation. So this WT is going to be the position so far. And so, maybe I'm at some position here. And I see some vector, maybe this one. And I need to decide whether I'm going to pick a plus or a minus. So we're going to define a probability to do this. So let's define some distribution. So it depends on the position and the vector. So this is going to output a +1 with probability. It's going to be a linear function of the inner product of my position and the current vector. And there's going to be some parameter C that we can choose later. Just So here we really want these numbers to be probabilities. So we need to have the assumption that the inner product is bounded by C. And in the analysis, we're going to pick C large enough so that this holds with high probability throughout the process. So what's the algorithm? So we start with W0 at the origin, and for T many rounds, first we check that this is indeed a probability that things are fine. So so if things are not fine, we throw hands in the air. So we're also going to make sure that this is always an upper bound for the discrepancy so far. So if any of these things happen, we just fail. Otherwise, we sample a sign from this distribution. And we update. So the next step will be previous one plus the choice. And we output the last one. So I want to give an analysis for this algorithm that's a little different from the one in the paper that a few different people have independently come up with. Let's see where I'm going to do this. Probably here. Okay. So what's the claim for the theorem? So what we're going to say is that for a choice of C, it's going to look like logarithmic in the input. This output is going to be square root C sub Gaussian. And the corollary, the prefix sums are all bounded, so these. Sorry, it's not the square root. So what does this mean? What is sub-Gaussian? So so we're going to need this this notion for us to talk. So I'll define it now. So random variable x is C sub Gaussian. Well, there's at least 3 ways to define this. I'll give you all of them. So you can say that essentially it means that it behaves like the tails are bounded by the tails of a Gaussian, and like it's upper bounded by a Gaussian in some sense. So you can say that this is a random vector. You can also define it for random variables, but I'll do a more general version. So it's going to be that this is bounded by for all vectors in Rn. So you can think about this right side as what you would get if you plugged in a Gaussian here. So it's essentially it's upper bounded by what you'd get for a Gaussian. There's a few other definitions. I'll give you another one that will come up later, but it won't be useful right now, but I'll just leave it written here. So I'll also need that the equivalent for all unit vectors theta. It happens to be equivalent up to a constant factor in this constant. For now, I'll just focus on this one. So let's see. So how do we prove this theorem? We're going to try to show this by induction. So recall what this is doing here. I'm at some position and I see a vector and I sample either plus or minus 1 and I move to that direction. So the claim is that if so let's see what is the current distribution. So let's denote by the big W of t. Denote the distribution of t of W of my current position. So we want to show that this distribution is square root C sub Gaussian. And we're gonna just keep track of an induction hypothesis that says that this is so the induction hypothesis is going to be that if I sample W here, so I need X, so I'll just W here. This is upper bounded by some a parameter sigma, let's say sigma squared, theta squared for all vectors theta. And then this sigma here, eventually we're going to have to pick it to be at least square root c. But let's try to understand why that's necessary in the proof. I wonder if everyone can see this, if you're sitting over there. Okay, good. So initially this is true. So in the base case, this is obvious because we start at 0, so that's fine. So let's see what happens if we take one time step, and we're gonna assume that things are nice and our inner product is bounded. Later we're gonna have to pick C large enough so that the inner product is indeed bounded, but let's assume that for now. So what happens here after one step? What we need to show is that if I sample some W here from the thief time step, and I sample some sign, let's just call it X, from this distribution, then this is still bounded. So what do I want? I want that. Let's just drop the subscripts to make life easier. We want that this is also upper bounded by the same thing for all vectors theta. Okay, so here's how we're going to do this. So I'm going to rewrite this as I can take out the W. And then there's some expectation in the middle. There's an exponential here. Okay, now I want to upper bound this thing in the middle. And if you think about it, it's not super intuitive what's happening because it's an expectation of a convex function. So you want to apply Jensen, but it's actually going the wrong way. But fortunately, there's a way to get around this. I'll just write it in this part of the board. Realize there's one behind it, but I already erased, so it doesn't matter. Okay. So here's the statement we need. So given a random variable, it's slightly more general than what we need, but it's easier to see this way. That's bounded. So you can think about it as the sign. So you can think about this as just plus minus 1. And some parameter. So this lambda is corresponding to this term here. Also, this x is inside, by the way. This x is inside the exponential. So here I have this expectation of exponential lambda x. So the Jensen would tell you that actually it's lower bounded by something. The Jensen would tell you that this is at least exponential of the expectation. So the interesting claim is that it's also at most almost the same thing. So I can just pull off the lambda from the thing, and then there's some extra term of lambda squared. And so this is actually kind of similar to what I just erased. If you remember the cosine hyperbolic, there was this bound that, if x is actually just IID, like a, uniformly plus minus 1, this is 0. And then you can bound the cosine hyperbolic by this term. But this is a more general result. I mean, it's not hard to show. I just really like inequalities like this. So the point is that you can reduce it to the case where x is supported on plus minus 1 by convexity, and then you just take derivatives and things magically happen to work out after something. So let's see what happens here if I try to apply this lemma. So here I have this same thing here. So here I apply the lemma, I get exponential. There's going to be the lambda. The lambda is just v times theta. The expected value of x, well, actually, I should not have done. So recall that x is sampled from this distribution. So the expected value of x is what is so it's plus 1 with probability this. Minus 1 of the other probability. So it's actually like minus the inner product over C. Okay, so back to applying this lemma. Okay, it looks like a little scary. It's still very far from what we need. But the point here is that I can try to remember what I have. So the inductive hypothesis says that I have an upper bound on this expression for any theta. So actually I want to collect terms that have W. Okay, so just do one more line and then I go to another board. So I can just rewrite this. So I want to collect the terms of W. So what do I have here? I have a theta. And then I have this minus W term. So it's gonna be V times V dot theta over C. And then there's some remainder here. And now this is something we know something about. So this is the expected exponential of W dot something, and we know things about W dot something. So let's see what we got. Okay, so I'm wondering if I should rewrite the last equation or not. I'll just keep going. So I apply this index hypothesis and I get, so there's no more expectation on W. It's just the exponential of sigma squared times the length squared of that vector. And then there's this other term. Okay, so let's see what happens here. So there's one thing that's nice. So notice that we want this, and it's hidden here. So there's a theta squared. Then there's this other stuff. And everything else has a v dot theta to it. So let's factor this term. And then there is a minus 2 sigma squared over c. And here there is a plus v squared over c squared over theta squared times theta squared. And there's a plus 1/2. And in order to finish, we just need to show that this is negative. Because we want an upper bound by this. So if this is less than 1, we're done. So the vector, notice that we're assuming that its length is at most 1. Yeah, so really, if you think about it, you just need to pick this to be large enough. So you just need to pick this term to be, much larger than C for this to work. Okay, there's the question of, okay, how large does C need to be? Okay, recall that our distribution relies on the fact that the inner product is upper bounded by C at all times. And we have this failure criterion for the algorithm here. So there are like, well, at every time step, I have like n+1 or 2 times n+1 constraints that I need to enforce. So, you can think about this constraint as being something like this. So all the coordinates need to be bounded. So, and if you believe that that this is the index hypothesis holds, then really I just need to pick the C to be on the order of a log nt, and then with high probability, none of these things will happen. I don't know if that was too fast or. Cool. So I want to mention one more. So okay, I guess the high level picture is okay. So here I show that there's an algorithm against oblivious adversaries that maintains all these positions to be square root log n t sub Gaussian. And the question is whether you can do better than that. Can you keep things just constant sub Gaussian? So there's another work that tried to get a little closer to that. So
So Victor, can I ask one
yeah,
question?
yeah.
So if you apply this algorithm to the case where the vectors are not oblivious, as in like the adversarial, do you recover the Spencer type result?
So if they're adversarial, I mean, the answer is no, but I'm trying to understand what in the proof break.
No, I mean, this bound is obviously too good, but I guess my question is, would you recover the Spencer bound?
So you recover it up to a square root log, I guess up to a log factor here. So you know the vectors are unit norm here. So in the Spencer case, they are square root. I guess there are two norms at most square root n.
Oh, of course. Okay, okay.
Uh,
I see. Okay, okay.
So you recover it up to the log factor. Yes, I think. And maybe y'all can correct me if I'm.
And then maybe like the other question that you were probably already thinking about, where did you use the obliviousness, or is it transparent where, for example, the proof would break if the adversary could choose a vector?
Right. I mean, it would. I'm still trying to think of like where exactly it breaks. Thinking. Yeah. So here when you pick the sign, so it's sampled according to this distribution. I'm wondering if there's some independence that I'm using here. So you know, maybe if the vector could be sampled depending on where I am, some of these steps would break. I'm trying to understand which, but
The random variables that you applied the inequalities on were just x and w, right?
that's right. Yeah, v here is not a random variable.
Right.
Or I think it could be, but it's just independent from the current position. Okay, so for example, this first step, here I pull off this exponential, right? Let me think, does that break if v can depend on w? I'm not sure exactly right now, but
What happens if the adversary just chooses V to be perpendicular to W, so like a no advantage?
yeah, so it can't do that because it's oblivious.
No, I mean, if.
Oh yeah,
Right.
right. If it were adapted,
And
right?
it would be a random walk, as in like each sign is clearly just random.
Yeah. Where exactly would this break? I also think maybe this first step might not work because you're pulling off this thing from the expectation that actually there's some dependence here on V and
Oh, right.
Yeah, V also depends on W.
yeah.
So in principle, if you take expectation over W, you're supposed to. No, but you're first taking expectation over X.
Right.
And W does not depend on X.
No, I think that's the issue.
It is.
Sorry, is X my current, what is the limitation? Is X my current position or what?
X is the sign, so W is the current position.
No, I don't, I see, W is the current position.
Yeah, so then it seems reasonable that you can take
The
expectation.
next vector should depend on W, that should be where the proof breaks, right?
Yeah, like V is a function of W, right?
Yeah, V is a function of W, that's the issue.
Yeah, and the adaptive setting, V would be a function of W, so you can't just pull off this W from the expectation. Because here, I guess here you'd also be sampling V somehow.
No, but you don't.
No, but the order is different. Like in some sense, you're taking expectation over X first. That's legit,
Right.
And then everything else is a function of W and V jointly.
Uh-huh.
But you're taking expectation over W, so I don't see a problem with the first equality.
So you're saying that the expectation over V is also here, right? Like it's over.
So V there could depend on W, yes.
Uh-huh. Okay, I think I see. So here, actually, so here I'm applying the inductive hypothesis to this vector, right? So this state is actually this.
Right.
And here I'm assuming that V is not depending on W. So there's no expectation over anything here.
I see.
So this is just for a theta that does not depend on W. So here, if V were to depend on W, then actually this thing would, yeah, I can't just apply some Gaussianity if this thing isn't this. Okay.
Good.
Yeah, I agree. Sometimes it's not obvious, like why the adaptive things don't work when it's oblivious. Okay. Where's the? So I want to quickly mention another paper of Young and others. I won't go into too much detail as much as I did in this one, but I want to mention it. So there's this Gaussian fixed point walk. There's the two Young, Sa and Sony, 21. So it's an algorithm for the same problem where you have these vectors from the unit ball, and I want to fight against an oblivious adversary. So what they do is the following. So they define a Markov chain on the Rios. With steps that are either 0 or plus minus 1. So the notation I'm going to use is, I'm at X. Then I go to X plus some the Markov chain step. There's going to be some parameter sigma. So the picture looks like this. I'm here and I'm at some position X. I either go to X plus 1, X minus 1, or I stay put. And they construct it so that two properties hold. So the most important one is that is the Gaussian fixed point. So meaning that if I have some Gaussian random variable and I take a step, it's still distributed as a Gaussian for if I serve some Gaussian distributed random variable. And I also want that the probability that I stay at 0 is small. So the probability that I don't move is actually upper bounded by some function of sigma. So in their paper, they're able to construct this Markov chain that has these two nice properties. I won't give you the exact transition probabilities because it's a bit messy. Well, it's pretty nice, but it will take a very long time to write down. And the theorem well, they showed a few different theorems. I'll just focus on one of them. That if I pick the sigma to be like 2 square root log of 2t, then I'll okay, I guess I didn't. Sorry, I should have explained what is the actual algorithm first. So let's do it here.
Actually, while you're paused, Victor, can I ask
Yeah.
what's the goal of this result again? Is it to improve on the parameters of ALS?
Yes.
Okay.
So yeah, so I'll describe what is their algorithm. It's different from the self-balancing random walk. So what they do is the following. So it's actually quite simple. So first I sample some starting position that's going to be from a Gaussian. It's a random vector. And then I'll take a step based on this Markov chain in the direction of the vector. So I'm just assuming that all the vectors are going to be norm 1 to make my life easier. It's not much different if they're not. So here what I do is I define the next position to be, well, I want to take a step here, but I want to take a step so in the direction of B. So it's going to be so here the picture is the following. So I have some can think about 2D. So I have some random variable here that's distributed as a Gaussian. So I want to keep an invariant that these are all Gaussian. I have some random variable here that's distributed as a Gaussian. I receive some vector VT. And then I think about WT. Well, it's a Gaussian, so I can write it as a sum of a Gaussian in this direction and a Gaussian in this direction. So, there's going to be some GV perp and GV. So the distribution is the same as the sum of these two. And then I look at just this direction, and then I look at this Markov chain that fixes the Gaussian. And when I take a step in this direction, I actually preserve this Gaussian here. So the next position is still distributed as a Gaussian.
I have a question about what you said that we want. Like G is like a multivariable Gaussian, right? So what does it mean to add like a real number to it?
Oh, sorry.
Oh, okay. Now I get it.
Sorry. So here it's actually multivariate. So in this part, it's actually I'm sampling from multivariate Gaussian. But notice that here I'm only looking at the direction of V. So I'm really only taking a step in this one-dimensional line. And then in the end of the day, I output, I just subtract whatever I started with. So there's this warm start, I guess. Okay, so what they proved is that such a Markov chain exists. And if I take sigma to be large enough, like square root log t, then all the positions are like 2 sigma sub Gaussian. But they don't state it exactly this way, but from what I gather, essentially they remove the dependence on n that this theorem had. Yeah, that's all I wanted to say about this result. If there's any questions, or I'll move on to a contribution. I'm fine to continue. Okay, I guess we can take a 5-minute break. Yeah. Okay. Okay, so for the second half of the talk, I want to give my contribution. So just trying to work with Janardhan, Kulkarni, and my Rothvoss. So here the claim is that it's the same setting, so I have some unit vectors given by an oblivious adversary. I'll just write OBL. And the claims that there exists an online algorithm that maintaining all prefix sums, so these WTs, the constant sub Gaussian. So in particular, if I only care about the largest coordinate, so we also showed this is tight, so there's a lower bound as well. So there's a strategy for the you need at least 2 dimensions. And the strategy will yield some vectors. So that essentially no matter what I do, Um, so after a constant factor, this is tight. First, I want to explain the lower bound. It's easier.
So
Yeah,
this is like for the maximal. Oh, okay. This is like for the maximal T inside big T. So this means that at some point in the algorithm, you will reach. You will reach like a very large maximal coordinate, but it doesn't necessarily mean you reach it like at the end of the algorithm.
that's right. Yeah, we don't know how to show a lower bound in that setting.
But it gives you like a particular like sequence of T's that you have like, or
So given the vectors, it just tells you that at some point with high probability, you will be large, but it doesn't tell exactly where.
oh, I see. So where it will depend on like the online algorithm itself, but it will always promise you some point that.
Right. Yeah, so first I want to explain this theorem. So essentially we'll use we had an adaptive lower bound of square root t that, that adversary could always pick something that's orthogonal to where we are. So we're going to try to do the same thing, except now we're oblivious. So here's the idea. Here's the proof. So the oblivious adversary will. So first I will split the time horizon into several blocks. Of some logarithmic size. So the picture is, I have the time steps, and I'm just going to have several blocks of the same size k. And the oblivious adversary will try something, try the same thing in each block. And we hope that at some point things will work out. So what will they try? So for each block, I will sample random signs. So I'll call them y. They're just random signs. And I will pretend that these are actually the signs that the online algorithm gives me. And the vectors I output, so I will output some vector vi or vt that's perpendicular to some of the previous ones. So this happens for every block, and then when a new block starts, it just goes over from the beginning. It just samples a new set of signs and outputs the same thing. And so the point is that, so say that the player outputs their signs. So in response to these vectors, the player will output something. The point is that with probability, well, So this is going to be probably 2 to the minus k. These will actually be the same. So, each sign has a probability of 1/2 of being the same. And so there's this probability of them being equal. And if this happens, then actually by the same idea of the adaptive adversary, this will be large. Well, not large, but not too small. But this is very small, and that's the point of trying things over and over, because if there's a tiny probability of something working out, but you try several times, and at some point it will work out. So the probability and this turns out to be large. Something like this. Some block works. And by work, what does it mean? It means that, maybe this block here, maybe this block will have a large prefix. That's not exactly what I promised, but actually the block is the difference of these two prefixes. And therefore, if the block is large, one of these two must be large as well. That's the idea. So now I want to try to explain this result. Maybe I will. So I'll give you, so first I'll need to define something called an epsilon net. Most of you probably already know what this means, but just to make sure everyone is on the same page. An epsilon net is a set of points. Let's call it P. And the unit ball, so that for every unit vector, you can find someone close to it. So the picture is like you have a bunch of points. And no matter what I pick, I can find something close to it. And that there's the greedy algorithm that just as long as there's still some point with so that the epsilon ball doesn't intersect anyone else, I include it. And if I just keep doing this, then the maximal set will actually have size at most exponential in 1/epsilon. It's not too hard to show. So here's the algorithm that I promised. I will, in the beginning of time, I will do a lot of pre-computation. Here's what I will do. I will compute a huge tree. So it has some root here. Every one of its nodes will have children labeled by an epsilon net. So actually the edges will be labeled by the epsilon net. So I will have some vectors here. And I put the same epsilon net under each one of the vertices that are not leaves. And I want this tree to have depth t, where t is a number of vectors. Okay, so here's the point of the algorithm. The player will start at the root. Whenever a player sees a vector v, it will ask, okay, what is a point in my epsilon net that is close to v? So maybe I have a v1 and there's a v1 prime here that is actually close to v1 within epsilon. So I move there, and then this vector will have another epsilon net down here. Maybe I see v2 and I pick something that's close to v2, and so on. Okay, so here's the theorem we need to make sure that this works. So we show that for any rooted tree, with vectors on the edges, there is always a distribution over the entire set of edges of the tree. So conveniently, there's a T written here, so I'll just use it. There's a distribution. D on the set of signed vectors on the edges with the property that all the root vertex paths are sub-Gaussian. So so here I take all the I'm just going to write SG for sub-Gaussian. And this is going to be true for all vertices of my tree. So, okay, so the point is that suppose such a distribution exists. At the beginning of time, I construct this tree, and I also construct this distribution on the signed vectors of my edges. And then what I do is I start at the root. I sample from this distribution. So I take some sample X from this distribution. So X would be a vector that has a plus minus one for each edge of my tree. So I see some vector v1. I move to some v1 prime that is close to v1. And then I ask, okay, what is the sign in X corresponding to this edge? And that's what I output. And then I keep doing that until I am at a leaf. And by this property that all the root vertex paths are tensor sub-Gaussian, no matter what the oblivious adversary had chosen for me, I'm always tensor sub-Gaussian for all prefixes. Okay, so I guess one thing missing is, okay, how do I actually construct or show that such a distribution exists, at least? Maybe I'll just come here. So in order to do this, we use some machinery due to Banach-Zych. So Banashek showed something. So we're going to take a bit of a long way to get to the distribution. So first we're going to compute a single sign over a tree. And then we're going to explain how we get from a single sign to a distribution over signs. So, but bear with me. Okay, so first, Banashek showed something for prefixes. Well, we didn't show it for trees, but we're going to get there. So here's what he showed. So he showed that if I have vectors, unit vectors, and if I have some convex body, so we're going to start going more geometric. So so I want some large convex body. So this is the Gaussian measure. So if you don't know what this is the probability that I sample from a Gaussian and I land inside K. So this is a standard Gaussian. And then dimensions. I want this to be large, almost 1. So the promise is that if I have such a setup, then there exists signs
Is that number 1 minus 1 over 2 times t?
That's right.
Okay.
So there are signs assigned for every vector so that all prefix sums are in a scaling of k, well, 5 times k. I want actually all prefix sums, so I'll write I equals 1 to t. And I want for all t and t. So this is still significantly different from what we need. The point here is that you can think about Banachek's result as something for a path tree. And eventually we'll get to something that makes more sense. I want to give the proof of this theorem because it's quite nice and it's we're going to have something similar in our setup. So in order to do this, Banashek showed a geometric lemma that's actually quite deep. I won't prove it, but I'll state what it says. So it actually was proven many years before by himself. So it's essentially a way to deal with this Gaussian measure. So it says that for a body K, you measure at least 1/2. And some vector U measured most 1/5. There exists a convex set that depends on K and U. Banashek denotes it as K star U. It also wanted to be contained in the union of K plus U and K minus U. And I want the measure to be as large as the original one. So I guess I can try to draw a picture. It's actually a little challenging, but so it looks kind of like this. So I have my convex set here. And maybe I have some small vector u. And then the challenging part about drawing is that I have to draw the same thing 2 more times. Let's see if I can draw the same vector. So the same convex body again. So let's try. Something like this, not really, but then something like this. So this is k plus u. This is k minus u. And then this convex set k star u, well, I won't really use the definition, but just so you have a picture in mind, it looks something like, it's something like this. So it's some, you kind of shake your convex body in some direction, and then you take 2, exactly. So I won't give the precise definition, but just so you have something in mind. K star u. Yeah, another thing I'll need is that it has large measure and it's contained in this union. So this lemma is actually quite non-trivial to prove. There's a lot of convex geometry, so I won't do that here. I want to explain how this theorem follows from this lemma. Maybe here. What is the theorem again? So I have some vectors v1 through vt in the unit ball and some large convex body, and I want to show that I can fix sign so that all the prefixes are in 5 times k. So here's Van Achter's idea. He defined a sequence of convex bodies starting from the last one. So the last one is just going to be the original convex body K. And in order to compute the previous one, well, I take my KT and I apply this operation to, well, I need to make sure that in the lemma, the thing has norm at most 1/5. That's the 5 here. And my vectors are unit vectors, I need to divide by 5. And then I also intersect with K. It's not clear at all why you do this. It's a very nice idea. So the claim is that all of these convex bodies have large Gaussian measure. So let's try to understand this. So we do this by induction. But induction backwards. So for t equals to the last one, well, the convex body is just k, so the Gaussian measure is at least 1 minus 1/2t, because that's the assumption in the theorem. Okay, so let's see. So how does this work? So so the step is that I want to lower bound the Gaussian measure of some kt. Let's say, okay. assume it's true for larger values of t. So what is this? The definition. Okay, so how do I do this? I want to lower bound this by, so here's the motivation. So here I know something about the Gaussian measure of this body when I take the star. But here I have some intersection. So it's really just some basic set theory that's I can write the following. So here the point is that if I have some vector in this star body, either it lies inside K or it lies outside K. So the Gaussian measure of this, the sum of these measures has to be at least the sum of the measure of this set. Okay. So by the this is at least KT. And this by the assumption on K, it's 1/2t at most. And then I just apply the inductive hypothesis. But the claim is following. I haven't proved the theorem yet. So okay, so I constructed the sequence of these convex bodies. And the point here is that the last one is still large. So last one still has measure 1/2. Okay, so the first or the last, depending on how you think about it. So okay, so what was the goal of the theorem? The goal here is that I wanted to pick signs so that all the prefixes are contained in the 5 times k. Okay, so how do I pick the first sign? Well, let's see, how do I continue? Maybe I'll just swap these two boards. Now I run into this problem where the upper board is not. Yep. Okay, so recall that we showed that the Gaussian measure of K1 was large. So let's think about what it means for something to have at least 1/2 Gaussian measure. Well, I claim that in this case, then it contains some large ball. Because if it doesn't, oh, let's think about it. So here's my ball. So if it doesn't contain, it's not contained in K1, then it means that, well, there's some reason for it. Maybe it's violating some hyperplane like this. So maybe if it's not contained in K1, then maybe K1 is contained in some strip like this. But actually, the measure of this entire strip is less than 1/2. So this is kind of the proof by picture of this small claim. So this means that by my V1, so there exists I want this to be true. You know, so here I started with, so like 1/5 is less than 2/3, so this is working. So I'm able to say that V1 is in 5 times K. Okay, so now I do some induction forwards. So here I assume I have some position WT so assume I already dealt with some prefix and I want to deal with the next one. So the assumption is actually going to be that it's in KT. So here I prove that it's in K1. But then by the definition of KT, what is this? So KT, by the definition, it's KT plus 1 star VT plus 1 intersect K. And by the definition of the star, this is actually contained in, well, there's a 1/5 here. Okay. So the point here is that I've picked some, I have some position that is in KT, but actually by the definition of the star, it's actually contained in either in plus or minus of the next one, which means that there exists a choice of signs so that the next one also works. I think that this is quite magical. I guess. Okay, so here I had something about trees. And so our claim is that we can generalize this theorem for trees. I won't give you the proof, but I'll give you the statement. Okay, so the claim is that so for any rooted tree, with vectors VE on the edges, and it's bounded by 1. So here I had measure at least 1/2t. I actually need in a convex body with measure at least 1. So it would depend on the number of edges I have. So it claims that there exists signs so that, you know, these are all inside 5 times K for all. So this is the root vertex path to I. So here the Banachik theorem is essentially for a path graph. And here actually works for any tree as long as you have some larger measure. And the proof is actually almost the same. You just, instead of defining the convex bodies like that, you kind of define the convex bodies as you intersect over all children. So, you know, if you have some I, you actually intersect over all the children of I. You take the, convex body at I, J, and you take this with the whatever vector is in the edge. And basically you run the same proof of this intersected body, and it turns out the same idea works. Okay, but this gives you a single sign. And here I promised you a distribution over over sign vectors on the edges. So the point is that
Sorry, isn't there another difference maybe that like every vertex there has a lot of children, so like you can't just do that? Or am I misunderstanding something?
so this is for any tree. So it could have a
Sure. I mean, if you're able to produce a single signing on that tree, you're also done, but like you can't do that, right?
So it's a little different. So here the statement is about subgaussianity, and here the statement is about a convex body. So it's not clear what you mean by a single sign.
Like if there existed, if for a large measure convex body K, you were able to produce a single signing, you would be good to go, right? I mean, you just can't. Okay, ignore the question.
I mean, I think we can do what you're saying. It's just it doesn't imply directly that there are distribution over signs that everything is subgaussian. I mean, it doesn't imply by what I'm going to talk about next, but I don't see why immediately having a single sign would give something that's subgaussian. Okay, so what's the idea of what we show? Let me try to. I guess I'll just move here. Okay, so let me try to prove this theorem. Okay, so I'll take my tree T. So here's my tree. It has some vectors on the edges. And then the point is that I will actually make a larger tree where every edge is actually divided into several edges. So, and so on. So each edge is cloned n times. And then I will try to find a signing for this larger tree using this claim. So we'll define some large K that has measure that depends also on the big N. I'll produce some signing, which, I still need to define what this convex body is. I'll find some signing on this larger tree, and then, so find and then I will sample one of these clones and set the vector to be whatever x restricted to this to this L clone. So the point here is that I have, for example, the first, so here I have this vector VE, and in this edge, I will write VE followed by a bunch of 0 vectors. In the second clone, I will put the VE in the second position, and so on, up to the last one, VE will be in the last position. Okay, so the point is that I'll find a signing that works for this larger tree. I will sample one of these different clones, and the distribution is exactly just what I get by restricting the sign to this, for example, the first clone of the edges. So, so the point is I have a way of computing one sign, and I need to turn it into a distribution over signs. So that's why I need to create this larger tree and sample one of these clones. I still haven't told you how this relates to Gaussianity. Well, the point is that this convex body K here, I can define it to be exactly what I need. So it's going to be a convex body in n times n dimension, with the property that if I sample one of these vectors, then this random variable is, say, Q sub Gaussian. So the point here is I have this larger tree, I sample one of these clones, and what I want to do is I want to guarantee that by doing this, the resulting random variable is, well, Q sub Gaussian. There's a 10 here because there's a factor of 2 and a factor of 5 from this here. Okay, so I won't have time to prove that. The only thing that's missing is to prove that indeed it has large Gaussian measure, and this turns out to be a concentration result. So the idea here is that, if I take random variables that are distributed as, well, I need to, the sub-Gaussianity here will come into play by this, this kind of variable here. So G is a Gaussian, and I sample something like this, and I want some concentration bound. And the problem is that these variables are heavy tailed, so I can't just apply Chernoff bound. What we end up doing is we consider some finite moments, and we use some analytic inequalities for this. So I don't have too much time to get into the details. I want to mention a couple open problems still. So this doesn't feel like the end of the road. I'll mention in this. So one is a Spencer in oblivious setting.
This means there's infinity bounded vectors instead of wall.
Yes. So here I can give the oblivious adversary gives me these vectors in the cube, and I want to pick signs so that the L infinity is bounded. And here the notion of sub-Gaussianity doesn't seem appropriate because we always pay the square root log for Gaussians. And it's not clear how you would rephrase this proof. Another problem that I like is can you get one sub-Gaussian? So this is possible offline. It's known how to do this in polynomial time offline if the vectors are all given to you ahead of time for the entire sum, not for the prefixes. And another more interesting question is, can we do this in polynomial time? Even for a constant sub-Gaussian, this algorithm I gave you is not polynomial time.
More questions?
So, like, do you have any idea how to make this poly time?
So it's been conjectured that like the self-balancing random walk, you could actually recall that we had this threshold. It was like the log of nt. If the inner product was larger than that, then it fails. Maybe you could actually get a much smaller threshold of like 1, and actually just deterministically move backwards if the probability falls outside 0, 1. I've implemented this in 2 dimensions, like it seems to work. Like if you just like actually do the process like in a computer, and it seems to be true sub-Gaussian as far as I know. But
When you implement, how do you choose the vectors?
when I implement, well, you can try something. I don't know. You can like you can try whatever you want, and it doesn't seem to to break. I don't have a good answer. So it's not one sub-Gaussian. So there are vectors that I can pick. Like for 3 vectors, there are specific choices of vectors that can be chosen so that in 2 dimensions, it's not one sub-Gaussian.
I see.
There are complex versions of this where instead of ±1, you could just change by a norm 1 coefficients.
I think, yeah, so I've actually thought about this before. So at least for the convolution setting, I've erased it, but I think for the convolution setting, there are specific, at least there's an instance where consider that the input is just a single vector, but it rotates. So imagine I have n vectors, so the first one is given, the next one it just rotates by 1. So it's just like a circulant matrix, maybe. And then it's just like this one comes here and so on. So for this kind of matrix, I can show that if I have complex numbers, there's a Fourier analytic argument that gives a constant bound for the convolution setting. But in general, I don't know if complex numbers help too much. There is a result due to CMU. I don't know if he's here, but that shows that if you could take 2-dimensional vectors, so I guess it's kind of like the same as complex numbers. If you can take 2-dimensional vectors, signs, I guess, then there's actually a fixed point Gaussian. Like essentially, you can preserve the Gaussian if you have steps that are 2-dimensional. So like the Gaussian fixed point random walk I showed to you doesn't actually, there's this probability that you stay at 0, so it's not exactly ±1. For that result, if you have 2-dimensional vectors, you can actually preserve the Gaussian exactly. I don't know if it's the same as complex numbers. I think it might be, but.
If you don't care about the prefix sum, you just care about the sum at the end, is it easier?
So there's an algorithm of called the Gram-Schmidt walk that does get this one sub-Gaussianity for just the total sum. However, it's not online, so it requires you to know the vectors ahead of time. I don't know if for an online algorithm that only cares about the sum at the end, is that easier? I'm not sure. Because that's, in some sense, you have to actually keep track of all the positions because you don't know when the thing is going to end. Like it's not clear, like if you know it's gonna end in T steps, can you actually, I'm not sure.
I guess one question I had is like, if you do this path and you only care about the end, I guess you could have taken independent. Right?
Independent size, no. So actually, I need to sample everything ahead of time. And so if I'm at some point, I need to condition, it's the signs are not independent. So they're all sampled ahead of time. And I just output whatever I sampled.
So I'm saying we just have one path instead of a tree. Then, like,
Oh, okay, I just had this one path.
yeah.
And your question is whether you can pick independent signs.
If you only care about the sum.
If you only care about the sum.
Oh, I see.
And then I'm saying maybe it makes it easier if you only care about the sum. I don't know.
Yeah, I'm not sure. Maybe.
Is this Spencer result algorithmic, or it's just says it exists and you have to try it?
So in 85, Spencer showed this existentially. And a few years later, Noga alone conjectured it's NP-hard to find such signs. But in 2010, Nikhil Bansal gave an algorithm polynomial time. So it took 25 years, I guess. It's based on semi-definite programming, and since then there have been other simpler algorithms to achieve this. Like right now, we know how to do this even in linear time at this point.
A very, very simple algorithm.
But not online.
Okay, so let's thank Victor again.